I'm just going to summarize briefly a nice review paper that just came out in Nature Reviews Earth and Environment on the impact of mineral dust aerosols on climate processes and climate change processes. As you probably already know, aerosols in general tend to have an overall cooling effect, but that cooling effect is very small, about 0.2 watts per meter squared. But the uncertainty on that is more than 200% with plus minus 0.5 watts per meter squared. Nonetheless, the processes are important, and it's fairly obvious that the warming is temporarily being masked by the increased dust loadings over time. This is just source and sink of dust in the global dust cycle, and it's showing emission fluxes in blue upward arrows and deposition fluxes in the downward orange arrows. The deposition can be dry deposition, wet deposition, and can have additional impacts in terms of the minerals contained in them, like iron, which can stimulate photosynthesis in the ocean in iron-limited regions and enhance CO2 uptake from the atmosphere as well, if the additional photosynthesized phytoplankton actually manages to sink out of the system and so on. The classifications shown here are hyper-arid, arid, semi-arid, and dry subhumid regions. So you can see dry subhumid region here, for example. And the fluxes are the largest from Sahara, so-called Dust Belt of North Africa, with 2,100 teragrams per year. And of course, Middle East and Central Asia has a high number of 1,400 teragrams per year, and Mongolian desert as well. And you have depositions on land happening here in the Tibetan Plateau, but mostly into the oceans and Amazon forest. Even smaller regions like the Chesapeake Bay here are supposed to have depositions of nitrate and so on, for example. As you can imagine, the uncertainties in these numbers can be very high as well, but there are global models which are constrained in many ways to be realistic, but nonetheless there are assumptions made on how the sources behave based on the seasons, wind strengths, vegetation cover, slopes, and so on and so forth. But keep that in mind as we look at what the net radiative forcing is defined as. The effective radiative forcing of the dust arising from the change in dust mass loading over pre-industrial to modern times, delta L P to M, can then be defined as delta F P to M, so that's the net radiative forcing at the top of the atmosphere, equal to R, some constant that is representing the net radiative processes, times delta L P to M divided by L, the mean loading. Use of the term radiative forcing here deviates slightly from previous work in which it denotes radiative perturbations entirely from anthropogenic forcing agents. However, because dust is natural aerosol, is a natural aerosol affected by climate changes and human land use changes, a radiative perturbation from historical changes in dust can be partially related to human land use changes, which is a forcing, and natural and anthropogenic climate changes, which is a feedback. These two contributions are difficult to disentangle, and so the entire radiative perturbation arising from historical changes in dust is referred to as the dust effective radiative forcing. Okay. Schematically speaking, what are the processes? You have dust interactions with radiation. So you have direct effects where some mineral dust aerosols absorb the short wave and some reflect short wave. In the long wave as well, coming from below, there are some which absorb long wave and then act as blackbody radiation up and down and all around. And there are some that reflect the long wave back towards the surface. If you look at dust interactions with atmospheric chemistry, you can have warming effect and cooling effect. So dust interactions with clouds can then occur through the mineral dust, which consists of atmospheric trace species having multi-phase chemical interactions and formation of salts with formation of soluble coating on top. The warming effects include a reduced atmospheric burden of anthropogenic aerosols. As we know, if we act aggressively and reduce the dust loading, which often is very good for health. Here, everything below 20 micron are used, so just remember that because they get airborne. Then the reduction of aerosols can reduce the cooling effects and cause warming. Secondly, reduced cloud droplet formation from small anthropogenic particles can also affect the dust interaction with atmospheric chemistry. Cloud condensation nuclei and condensation density can all matter as well. Okay, cooling effects: reduced or increased atmospheric burden of reduced atmospheric burden of coarse mode dust and increased accumulation of coarse mode dust can have a cooling effect. Reduced atmospheric burden of O3, ozone, in the troposphere can have a cooling effect. Increased water absorption efficiency of mineral dust is going to have a cooling effect, and reduced ice nucleating abilities. Ice particles in the clouds or in the atmosphere can have reflecting or scattering effect, which ends up cooling the overall temperature as a part of the impact of mineral dusts. I'm getting somebody here, so give me 1 second.
Sorry, this is going to be a jump also in terms of sound, because I was using the microphone from the computer, but I switched to the headphone here. So I want to just make sure that the cloud, the ice nucleation that we are talking about here is in the context of atmospheric chemistry and not in the clouds, even though there is chemistry of the clouds as well. So dust indirect effects on warm and mixed phase clouds can be looked at this way. Dust-free environment has a certain albedo, so incoming shortwave is reflected partially here. In a dusty environment, you can have increased cloud condensation nuclei or cloud droplet number concentration as well being higher, so that albedo is increasing, which will reflect more of the shortwave. You can see the relative thickness of the arrow here. Or you can have reduced cloud condensation nuclei and cloud droplet number concentration, which will have a lower albedo, in which case you're reflecting less of the shortwave compared to the dust-free environment. Obviously, these are very schematic, and the story is always very complicated and very region-specific as well. The dust indirect effects on mixed phase clouds, then in a pristine environment, you have liquid particles and ice particles mixed in, as we mentioned before. Dusty environment can act as a condensation nuclei for ice particles, and then more cloud ice and less cloud water can lower the albedo, resulting in warming. So again, you can see that less of the shortwave is being reflected here in the dust indirect effect on mixed phase clouds. Looking at dust indirect effects on cirrus clouds, which are high thin clouds which tend to allow shortwave to come in and tend to absorb more of the long wave going out and act as a warming agent. So homogeneous nucleation in a pristine environment can reflect almost all of the sunlight but absorb outgoing long wave radiation. If you have heterogeneous nucleation, then less of the short wave is reflected, as you can see with the thickness of the arrow again, but more of the long wave is allowed to go out. So it depends on which clouds you're talking about. In a dusty environment, fewer ice crystals can create more outgoing long wave radiation. So similar amounts of shortwave reflection. So that means you will have a cooling effect, whereas if you have more ice crystals with less outgoing long wave radiation, then you can have a warming effect. Here you have less reflection of the short wave that's coming in. Okay, dust semi-direct effects on low clouds. If you have dust above clouds, so negative dust indirect effect, so semi-direct effect, sorry, SDE is semi-direct effect. Enhanced temperature inversion, so increased cloud cover. So temperature inversion is basically where you have the tropospheric lapse rate having an inversion or a kink. Dust within the clouds can produce positive dust semi-direct effects, so increased cloud cover, enhanced cloud evaporation. And dust below the clouds can have negative dust semi-direct effects and increased cloud cover here as opposed to here. So you can see the temperature effect, cloud cover effect, and cloud cover effect based on where the dust loading is. Obviously it's never all above, all in the clouds and all below, so you have to see what the net effect will be given the circulation and how the dust gets distributed in a particular region. Here enhanced vertical motion and low level convergence can happen, and you have more, so you can see the reflection of shortwave is changing here as well. So some is getting absorbed and is reduced, what is coming in here, some is getting reflected, and what goes out is reduced. So here you can see how enhanced cloud evaporation, waters in the water content, etc., can affect shortwave reflection, and so on and so forth. So follow up on the details. Each particular kind of cloud interaction will have many papers that are provided in this reference article. When you look at dust interactions with the cryosphere, so clean snow in a dust-free environment has a certain albedo, and it can absorb some of the radiation, shortwave radiation. But if you have dust polluted snow, then you have reduced reflection and enhanced absorption, so the melt rate can increase, and you can have more complicated interactions if you form ponds of water which have even much lower albedo. But here we are only talking about dust interactions and not those cascades of interactions. Dust interactions with biochemistry can be very important. So ocean dust deposition can act as ion fertilization, as I said before, and can increase the CO2 uptake. And increased ocean dust deposition can have enhanced oceanic productivity. Sorry, this is the control, and this is the increased ocean dust deposition, where you can have increased CO2 uptake. We know that ion fertilization works, and most of it comes from aeolian deposition and so on, but whether these additional photosynthesized phytoplankton and the zooplankton and so on actually end up enhancing export and increasing CO2 uptake or sequestration is not always obvious. But to the extent that photosynthesis can be enhanced by ion fertilization, you can expect increased CO2 uptake. Okay, so global mean radiative effects and forcing of dust at the top of the atmosphere. Then you can look at dust related perturbations. So direct radiative effects we are looking at in terms of radiative effect or forcing in watts per meter squared, cooling effect when it's negative, and warming effect when it's positive, and each one is provided with some sense of the level of scientific understanding. So shortwave forcing of the direct radiative effect is a cooling effect, but you can see the standard deviation or the error is very high. For the long wave also its uncertainty is high, but on the whole it's a warming effect, so it's a net forcing of the system. Overall, you can see that it may be a small negative number of order minus 0.2, but the uncertainty is order 0.5 watts per meter squared, as I said before. And the understanding of all these is medium on some relative scale of how well we understand the processes. In terms of dust-mediated cloud radiative effects that we discussed, warm clouds basically equal uncertainty on either side of 0 with low understanding. Mixed phase clouds may be slightly warming, but uncertainty is high with understanding being low. Cirrus clouds have a cooling effect, but uncertainty is high and the understanding is very low. And semi-direct effect has a slight positive effect, but uncertainty is high, understanding is low. Getting to other radiative effects like atmospheric effects on aerosol, direct radiation effect, very low understanding with large uncertainties, cryosphere, low understanding with some uncertainties, biochemistry, again large uncertainties but is expected to have a cooling effect with maybe enhanced CO2 uptake, and effective radiative effect overall is negative but large uncertainty, and effective radiative forcing is also small, negative but large uncertainty. So take these for what they are worth, but this is the state of the art. Just to look at drivers of historical dust loading increase which has been observed. Large historical increase in dust can be linked to natural and anthropogenic climate changes or human land use changes. Observations indicate that dust is highly sensitive to climate. Indeed, dust increased 2 to 4 times between the interglacial and glacial periods. So if we go back to the ice age cycles, there is evidence from ice cores that dust loading increases during cold periods. Overall precipitation is reduced, land is drier, vegetation may be lower, vegetation cover, and dust loading goes up. Dust loading has varied a similar amount in some regions owing to 20th century climate variability. As such, changes in aridity, vegetation cover, and wind speed arising from natural climate variability could have driven the long-term increase in dust loading, at least in part, as suggested for North Africa, where we have the Sahara and the Dust Belt. Anthropogenic changes to climate and atmospheric composition could have additionally affected dust loading through changes to aridity and plant fertilization. So I won't read all the details here, but you can go and follow up on the box that is provided. If you look at the atmospheric dust mass loading changes since pre-industrial times, we're going from 1850 to 2000 or so, and globally atmospheric dust mass loading in teragrams has increased, but you can see the uncertainty is high. Over Asia, a similar story, and there is some satellite evidence showing that a greening has happened over a large part of China and India. Whether that's forest cover or agriculture depends. China has had much more vegetation cover increase, whereas for India most of it may have been coming from crops, because it's looking at leaf area index and not necessarily separating vegetation types or crops and so on. But nonetheless, atmospheric dust mass loading in teragrams has gone up, and these are the changes from pre-industrial levels. Here in both cases you can see can be as high as 40 to 70% or so, and here the scales are different, so you can see that maybe even after the decrease it's 40% higher compared to the pre-industrial level, and may have gone more than 100% above the pre-industrial level, even though uncertainties are remarkably high. North Africa again has steadily increased since the 1910s or so, and there is some evidence that it had a very long stretch of droughts. For a while it was debated whether that was related to grazing and human land use, and then it turned out that maybe that was related to ocean warming, which itself was related to activities in the developed country rather than local activities in North Africa itself. Southern Hemisphere, obviously much smaller range, but still it shows some increase in terms of percentage and absolute loading in teragrams. Okay. Climate model representations of historical changes in dust loading. Changes in dust loading relative to 1841 to 1860 from the dust reconstruction and 12 CMIP6 models with prognostic dust aerosol cycles. So many models do aerosol cycles with source sinks parameterized in some ways how good they are. This is the point of comparing. CMIP6 data are 10-year running means for historical runs. Gray shading denotes the 90% confidence intervals for the dust reconstruction. All models and the ensemble mean fail to reproduce the large historical increase in dust loading. So you have to always remember this when you look at model rendition of internal variability like El Nino, La Nina, and the anthropogenic warming, and the even when there is dust aerosol cycles being done prognostically in the models, how they do the direct effect and indirect effect in terms of cloud microphysics and so on, and just radiative effects is very tricky business. So here are the observational reconstructions with their own large uncertainties, and then you have models all over the place with this one here. I think it's the HAD-GM3 here to make sure, has some heavy peaks happening here in the 1950s, which has to be checked in detail if you're interested. So it's a very brief introduction. It's a very nice review paper you should read up if you're interested, and has a very nice long list of references as well to follow up on each of these feedbacks. But nonetheless, climate change and global warming are being affected by mineral dust loading, which by all indications has increased over the globe and over subregions like Asia, for example. Okay.